Please, you can start again. Here. Reinhard. Thanks.
So I hope you are already awoke. You got up this morning. Yesterday we had some pattern formation. Now today we are going to the flow in ferrofluids, turning to the flow in ferrofluids. And I tried to best to make this morning's motor karaoke as variable as possible. So we had a flow in a capillary and we applied a constant magnetic field, and this now hinders the rotation of the particles in the flow and creates some additional viscosity, which is called the relative viscosity or reduced viscosity. It's just the viscosity change due to the magnetic field over the standard viscosity of the liquid. So, and this can be described by this rather handy model. Now the question arises, what happens if we apply not a constant magnetic field, but if we apply an alternating magnetic field, let's say in the direction of the pipe. And there was a conjecture by our friend Mark Schliermis, a famous Soviet scientist nowadays working in Beersheba in Israel. And he, together with his with Konstantin Morozov, he wrote an article in 1994, Negative Viscosity Effect, that is just that they predicted that if you have an alternating field with a certain frequency, you should be able to put in energy into the flow, so that these tiny magnets are kind of nano motors which speed up the flow. So if you somehow the alternating field frequency fits to this rotation speed, there should be a kind of reduction of the viscosity. And for that he suggested a pair of coupled equations, which I'm not here to explain you in detail, but what I want to say is that there are here some factors tau b on front, and that is important for our understanding of this field. So what is tau b? Well, tau b is a relaxation time of the magnetic particles in the liquid, and I will explain it more in detail. The point is, here you have the magnetic particle, and you have the magnetic moment attached to the magnetic particle, and then you have some tensides, and eventually this is somehow the volume of this whole configuration, and here around you have the carrier liquid. Now you are rotating the green field, well, this is a magnetic field, you are changing the direction of the field, and then this magnetic particle will follow somehow, but this takes some time, and this time will become even longer as with an increase of the viscosity of the carrier liquid. And it also will increase if the hydrodynamic volume, which is somehow the volume of the particle including the cover, is increasing. This is rather standard, that you have such a friction. So this is called the Brownian relaxation time. So we would be happy if this is all to describe the interaction of the magnetic particles with the liquid. But unfortunately, reality is more complex, and we have a second relaxation time, and I try now to describe what this is doing. This second relaxation time is called tau n, and it's called the Néel relaxation time, and this is governed by the magnetism of the particle. So you have here a factor which is rather small, 10 to the minus 9 seconds. It's a so-called Coringa relaxation time. Then you have here another factor, and this is in the exponent. Well, it's crystal anisotropy. So for increasing anisotropy of the crystal, this magnetic moment sticks better and better to this magnetic particle. This is also true if you are increasing the magnetic volume. That means for small particles, this volume is rather small, and it is certainly smaller than just the mechanical volume of this particle, because there are also some boundary layers where magnetism is not really so active. So in another, and that is now what's happening, and going back, that often you don't have the situation that the magnetic moment is fixed to the magnetic particle, but somehow it can rotate inside the magnetic particle. And this depends on the size of the particles. If you have huge particles, you see with this exponent, it's going, this upper part is becoming really large, and certainly then this time is getting very long. And but on the other case, if you have just standard magnetite particles, let's say of about 5 nanometer diameter, then this factor is because this factor is very small, this time is very short, and that means that this this magnetic moment is following is following the outer field without turning the particle. This is something which I would say in an egg model is equivalent with a raw egg, where you rotate the inner yellow, but due to the glibbery outer white of the egg, you don't have any friction, and the outer shell of the egg is not rotating at all. On the other hand, the above case is where the magnetic moment is completely fixed inside the magnetic particle. This is the case of the hard-boiled egg. So you rotate the yellow egg and the outer shell has to follow. And this is the case where the Néel relaxation time is much larger than the Brownian relaxation time. This is the ideal case for easy understanding of interaction of magnetic fields with the flow. And one says that these particles are Néel blocked. That means that the Néel relaxation time is blocked, it's not important anymore. And this is true for some magnetic particles like cobalt or cobalt ferrite. Why is it in this case? Well, cobalt and cobalt ferrite, they have a very large crystal anisotropy, and that makes it at diameters of maybe 6 nanometer or so, there is already a blocking of the magnetic moment. But if you are working with magnetite, you are either in this part here, or you are someone in a soft egg regime. That depends on the size of your diameter. And then remember that if you have a size distribution, that some particles will be raw eggs, and actually it's most of them, the small particles, and only a few large particles will be hard-boiled eggs. So this makes the situation quite complicated. Now, to a quantitative investigation of the negative viscosity effect, we performed an experiment to measure this negative viscosity effect, and because we were only the second, due to some misunderstanding, we had to do it very quantitatively. So you have here some kind of pipe with a reservoir, and then you have this ferrofluid, it's now blue, and it's flowing through a solenoid and then to a second capillary and into a second reservoir. Oops, that's too fast. And then one has to pump it back. This is not in the plot here. So we are creating a continuous flow, and then we are measuring the pressure drop across this capillary and the pressure drop across the reference capillary, and by switching on and off the magnetic field here in this upper capillary, we can calculate from these ratios of the pressure drops the reduced viscosity. So this is handy because if you have a continuous flow, you don't have to empty and clean and so on. So you can measure for hours. So what we did is we applied alternating fields in a regime from 1 kilohertz, which is top 1000 hertz, 3000 hertz, 6000 hertz, 9000 hertz, 14,000 hertz, and 22,000 hertz. In between as well, but for you, I don't show you these curves. And so you see that for a certain frequency regime, let's say for example the 2200 hertz, 22 kilohertz, you see here a viscosity reduction. It's only a reduction of about 1%, but it's a clear viscosity reduction. So this is the so-called negative viscosity effect. And the curves here are fit by integration of the coupled differential equations proposed by Mark Lewis. So this is a quantitative comparison between the model and the experiment. It's a rather cumbersome fit, but as you see from this plot, it looks very nice, the agreement. Now, this has been published, and now we have a look at this Brownian relaxation time. Well, here it is. You see, this is the Brownian relaxation time as a function of the frequency, which were extracted from this fit. I told you that the Brownian relaxation time is completely determined by the viscosity eta zero, the hydrodynamic volume, and kBt. So it's purely geometric. It should not depend on the frequency. So this is really mind-boggling. It should be constant. It should really not depend on the frequency. We have somehow mismatch between model and experiment. The model can nicely fit the experiment, but the fitting parameter is frequency dependent. This is not nice. Mark would say the problem is that the magnetic particles do not behave like hard-boiled eggs. Well, I plot you the inverse of this fitted Brownian relaxation time, and you see that it somehow is a function of the frequency, and it can be fitted by some efficient Brownian relaxation time. The efficient Brownian relaxation time is some geometric or this kind of fixed relaxation time times a factor gamma and the driving frequency. So you have a very quantitative function, functional dependence between driving frequency and an effective Brownian relaxation time. So far we have not a complete understanding for this effect, but I would say a rather easy, well, ad hoc explanation for this effect is that you have agglomerates, especially because that was a water-based magnetic liquid, and water-based magnetic liquids are very fond of making agglomerates. And now, here is a blackboard. If you have two magnetic particles and you apply a magnetic field for some time, say if it is a strong magnetic field, these particles are building up a chain or two, some more particles are building up a chain. So this particle is getting a larger volume, a larger hydrodynamic volume. And now if we assume that if you are alternating the magnetic field, for example now it's going off again, or since you have a frequency like that, so in another case you have a frequency like longer, a lower frequency, then there you have a longer time and a longer period, and then you can build up here larger particles, larger agglomerates than just in such a short time. So if you assume a linear dependence between the size of the magnetic agglomerates and the period length of the driving frequency, then you are getting an explanation for this frequency dependent Brownian relaxation time. Well, but the main message is that for a microscopic description you need to know a lot of information about your ferrofluid. And this is not very nice because you don't have monodispersed liquids, and you don't know for sure the size distribution, just you can measure, but then you don't know how these agglomerates are forming and so on. This makes the situation quite inconvenient. So, another friend of us, it's Mario Leo, he favors a macroscopic description. And this macroscopic description somehow convinced us to perform another experiment with a rotating field. To be fair, Mario is not the only one who is able to give a macroscopic description. Also, Max Lewis has another macroscopic model aside of his microscopic models. One early experiment on rotating magnetic fields is a nice article by Mr. Tsvetkov. And I show you this picture because you are here in the Department of Complex Fluids. And this is a nice article published in 1939 when Soviet Union was not yet attacked by Germany, and then it was still published in German in the Acta Physico-Chemica of the USS. So this is a Soviet publication in German, and you see how this guy Tsvetkov applied a rotating magnetic field. He had some permanent magnet, and this was driven by a motor here, and then you had here some connections with mercury and so on, and he could measure here some torque. So it's a very early nice experiment, but he did not measure the impact of a rotating field on ferrofluids, but on liquid crystals. And he observed that a rotating field spins up a flow in liquid crystals. So this idea at least was later adopted by Moskowitz and Rosenzweig, and they found also a rotation, well, they found an interesting effect but didn't understand it, that the rotating field spins up a flow. So there was not a quantitative description of that effect, and also they could not predict the direction in which direction the flow is flowing. So together with a patent by Mario Leo on a magnetic pump, this gave us the idea of a different setup. So we have here a channel, and you have a magnetic liquid in here, and then we are applying a rotating magnetic field, and the rotation is going in that way. It's not horizontal, but it's like a rolling wheel. And this creates here a magnetic stress at the surface and spins up a flow. And the geometry is in that way, and now I'm back to biroid. We have the ring, the biroid ring, and it is an annular geometry. You have here an annulus, then you have one toroidal coil. Here you see the channel filled with ferrofluid, and then we have another cylindrical coil, solenoid. And by applying here an oscillating field and another one, and both fields are somehow out of phase, like that, you are creating a rotating magnetic field. You see that these fields are out of phase. By the way, this is Mr. Kraus. And here you see the impact of such a field. Here we have a small ship, and you see that the ship is flowing with the flow, and the ship is a small part of plastics swimming on top of the ferrofluid. And switch it on again. So you see that you can excite a spontaneous flow by a rotating magnetic field. This is not possible with an alternating field. There you get only a viscosity reduction. Here, the reduction of the viscosity is so large that you get a spontaneous flow. Now, how can one understand that? Well, first we measured the flow velocity as a function of the applied field strength for one driving frequency. And you see that it's going with the square of the applied field. Then we measured the flow velocity for a channel of 10 millimeter diameter as a function of the driving frequency. And you see that here is a maximum, and then you are getting a decay. Then you can perform this experiment for a smaller ring, a channel of 5 millimeter, and a smaller ring, a channel of 2.5 millimeter cross section. And to get rid of the depth of the ring, you can scale this experiment by L, which is the depth of the ring. So you get kind of reduced flow velocity, and this is also divided by the square of the magnetic field. It could be H, G is just saying that we are measuring the field far away from the magnetic liquid. So this kind of scales out the geometry, and Max says that we are measuring the maximal flow velocity. That means we are measuring the flow velocity in the center of the channel. Now we need a model for that. So our model has a square cross section of the channel. Then we have a coordinate x, coordinate y, z, and this model is translational invariant, so that the curvature of the ring is not taken into account. We assume that we have a very large ring, so the curvature is not of importance. Then we have a flow velocity only dependent on x and z. Then we assume that there is no acceleration, that we have a stationary flow. So that we switch on the field and wait for a long time until everything is stationary. And then we assume that the velocity at the bottom is 0, and also the velocity at the side walls is 0. And on top of this channel, we have magnetic stress, which is driving the torque, which is driving the flow. It's a cross product of the magnetization and the applied induction, and this gives actually the decay, or describes the decay of the velocity with the depth of the container. And if you calculate that model, you get that kind of flow distribution. So red means fast flow on top, and then blue means low velocity. Now the question is, how does this flow velocity, especially here this maximal flow velocity, depend on the frequency? And this is now where a macroscopic description is important. So, in order to know something about our magnetic liquid, we've measured the AC susceptibility with a simple setup. We have another torus where you can remove these connections here. And then we have a second coil, which is here in this channel. It's just a winding of about some 100 windings. This is a coil. This is connected to a lock-in amplifier. And here you have the frequency generator. And a high power amplifier and some load resistor. This gives you the reference signal. And this lock-in amplifier, now you measure for every frequency, for each frequency, the signal, first for an empty coil, and then you immerse ferrofluid in it, and in this channel, and then you measure the response for a filled coil. And the advantage of this setup is that it's free of calibration, because you have a circular duct, so the demagnetization factor is not, you don't have to take into account, because it's an infinite container. It's not a short coil or something like that. So here you see the results. These are the susceptibility curves. So this is the imaginary part, and the square is the real part of the susceptibility. Probably this is maybe not so, you're not so acquainted with it, but you might notice as well from the dielectric constant. It has a real part and an imaginary part, and the same is for the susceptibility. It has also a complex susceptibility, and for very low frequencies you see, you see that the imaginary part is 0. This is the initial, somehow the initial susceptibility we had in the beginning. So for this liquid, we have a rather high real part of the susceptibility. It's about 8, and that is because it is a cobalt liquid. So this has a very high real part, and much more important, it has also a huge imaginary part, which is about 3 or so. And now here we have the general flow velocity, the rescaled flow velocity, and by macroscopic model, given as well by Mario as well as by Mark Schlumis, you get such an expression. Now in this expression, you have here a combination of the imaginary part and the real part of the susceptibility. stability. So you have here a product. This is very important because due to that product, you have to have both a high real and imaginary part. Here you have again a square of the real and imaginary parts, and n is some kind of demagnetization factor. And alpha is also some kind of factor you have to calculate. Well, so we want to make a comparison of this model with our experiment. So we took here the real and the imaginary and the real part of the susceptibilities, and we're plugging it in this equation, and of course then you have to calculate alpha and n, and then you end up with this black curve. So this black curve describes the frequency dependence only by the real and imaginary part of the complex susceptibility. You don't have to think about Brownian and Neal relaxation times. It's just not important. You're just measuring the complex susceptibility, and you don't have to care about how this complex susceptibility is somehow coming together. You measure just the outcome. It's like measuring temperature. You don't have to care about how the particles are hitting each other and how they interact. You don't have to care about statistical mechanics. You're measuring a macroscopic observable, and with this macroscopic observable, you plug it in this macroscopic description, and out comes the proper velocity of the experiment. So this is a good message that you don't need a macroscopic description, or much better is often a macroscopic description of these experiments. Well, a nuisance of this experiment is that you somehow have to track the flow velocity in this black channel. And I showed you this ship, but this ship has a disadvantage because it's rather macroscopic. It has some 2 or 3 millimeters diameter, and we want to make it as good as possible to the theory, and so we needed smaller particles. And we tried about 20 different types of particles, and nothing worked. The PhD student already was very desperate. It was a long project, and he was, doing like that. And then some part of his skin of the head was dropping down. So this is called in English Dandorf. I don't know the Portuguese word. It's a part of your scalp skin, and was falling down, and somehow it nicely swims very well on the ferrofluid. So this is a nice way to make a particle image velocimetry, but of course you don't want to spoil the skin of your students. So I thought, well, can we do another experiment where it's much easier to measure the flow velocity, where you don't have to immerse these particles, and also where the demagnetization factor is almost the same, notwithstanding of the direction of the field. In the channel you have this rotating field, and if the field is in line with the channel, you have another demagnetization factor than if it is orthogonal to the channel. And this makes the comparison with experimental theory a bit cumbersome. So what we did is we were immersing a drop of ferrofluid, and then applying a rotating field, and then the rotating field spins up rotation in the drop, and the drop is swimming like a ship with a paddle wheel. Here again you see that the drop velocity is increasing with the magnetic induction, and here we have a side view from this drop, and our colleagues in Oldenburg, they calculated an analytic model based on a half drop solution, and they had to make it with this half drop because of some symmetry considerations. And here you see that the rotating field is increasing here a flow, a circular flow, and this flow interacts with the underlying liquid, with the transparent liquid, and accelerates this liquid, and this propagates the droplet. So now the outcome of this analytical model is also a macroscopic model. Is you need here the viscosity of the drop of the ferrofluid, and you need the viscosity of the underlying fluid, the supporting fluid, and then of course you need here the complex susceptibilities, and then you are getting the drop velocity. And here you see that we don't have any fitting parameter, so experiment and model surprisingly fits. And we were quite astonished. And I don't know why this is so good, this agreement. Because there are all kinds of shortcomings, you know. We don't have a completely spherical drop, then this model is only taking into account a specific kind of flow. But it seems that this microscopic inner structure is not so important as long as the outer flow velocity is suitable. So, now once we had that, we were also interested on the frequency scaling of the drop velocity. And here you see a new experiment performed by Fabian Lidwig. We have a cubicle with 6 different coils, and then you can apply a rotating field in all directions. And here you see again the analytical formula. It's the same formula I've shown you before. And now we have the problem to produce drops of the same size. You take a pipette, but somehow the drop size is not as constant as you like. So what we did is, we did 2 types of measurements. We measured the drop velocity at a certain frequency at 500 Hertz, and then we measured the drop velocity at a different frequency where we were interested in. And by rescaling that, you see that the first part is falling out, and we are ending up with the second part here. And this ratio of this complex susceptibilities is now plotted as a function of the driving frequency. And you see the red curve gives you the predictions by the model, and the circles are the outcome of our experiment. So once again, it seems not just by accident that we have an agreement of model and experiment. So I have 15 minutes left also. That it's okay, that's fine, that I think I can manage. The last chapter is a traveling field. And as often you have an idea and you think, oh, okay, that's new, nobody did that before. So you perform the experiments, you get some results, and eventually you realize there has been some experiments before. Mostly, in most cases, these experiments are different and have different consequences. So I show you. This is a traveling field. So you have a spatial-temporal modulated traveling field, some kind of sinus, which is shifting. There was, in a closed rigid duct, article by our colleagues from Yale University, Hugh Köser, and this was published in Nanotechnology. And this is a sinusoidal traveling field in a completely closed duct, and it drives some flow if you have very high driving frequencies. So these are driving frequencies in the ratio of the inverse Brownian relaxation time, so a kilohertz machine. This is not what we did. Then there is another thing. There are closed flexible tubes. So you see this red pipe you have maybe in your garden or so, of elastic rubber tube. And then by some Korean scientists there was an experiment where you have different coils and you are activating these coils, and then these coils are attracting ferrofluid, and in this area then this flexible tube is squeezed, and by switching on different coils you can now push this squeezed tube, or you can push, you can drive flow by this wandering field. This is a very low frequency mode, and this is a very engineering application. Was published in 1999, and we are coming more to our experiment nearer. This is a free surface, and in an early article by Kikura, Sawada, Tanahashi and Seo, said these guys had a free surface, a channel filled with ferrofluids, and they activated a set of coils and could drive flow in that way. Okay, this is history. Now, yesterday I showed you the dispersion relation of a free layer of ferrofluid, and I showed you that this free layer is getting unstable, then you are getting the Rosenzweig instability, you are creating here a kind of a wave number or wavelength, and then you can switch back. And if you switch back, so the liquid relaxes, and you have in the undercritical field a propagating surface wave. This is a propagating surface wave, and you can measure here. This is the radius. Here you have the time. You see that here some waves are propagating in a circular dish, for example. Now, what is interesting is that this wave propagation is scaling with the distance from the critical field. Here you see that the critical field or the critical induction is approached. It's about 17 millitesla, and here is a square of the propagation velocity of these waves. And you see that this propagation velocity nicely scales with distance from the critical induction. So that is something you have to keep in your mind. And now what we did with this in the background, we constructed the following setup. You have here an open dish filled with ferrofluid. Here you have your Helmholtz pair of coils, and now the green stuff is a belt. This belt is from a security belt from your car, and in this belt you have pockets, and you see that there are some iron sticks in these pockets. And here you have a motor, and this motor is now driving this belt, and you see that if you have a fixed sensor, Hall sensor, as these sticks are passing by, you have sinusoidal modulated strength of the magnetic induction. So by this kind of system you are creating a traveling magnetic field. By the way, this is Achim Beetz, who did this experiment during his PhD thesis. Diploma thesis, sorry. Anyway, Here you see the setup, and you see some kind of traveling waves. And now we were interested in the amplitude response of these traveling waves for a certain applied magnetic induction. And we used a laser, and we measured the reflection of this laser, the amplitude. And here you see the amplitude of the laser reflections as a function of the driving frequency for a certain applied constant induction. So you apply a constant induction, then you are driving the flow, and then you see here you get a maximum. This is a maximum because you have a resonance of the driving velocity of the belt with the propagation velocity of the free surface waves. So it's just a resonance phenomenon. And now, by increasing the constant magnetic induction, we are approaching more and more the Rosenzweig instability, and that means that this resonance frequency is becoming slower and slower. That is because the propagation velocity is becoming slower and slower as you are approaching the critical field of the Rosenzweig instability. And now we have here a scaling of this resonance frequency with the magnetic induction, and this can be described by some formula where you exploit the nonlinear dispersion relation of the magnetic liquid. So this fits quite well. Now we were interested, you have a propagating wave, and in resonance this propagating wave is getting large. Not necessarily is it the case that there is a flow. You can have a propagating wave, but this doesn't have to drive a flow. So the next question is, does this wave drive also a flow? There is a potential flow, or the potential flow, where you only have waves going up and down, but they do not propagate liquid. So in order to test whether a transport of liquid is accompanied by this propagating wave, we use now a second setup. Once again, we are using X-rays, and you see that here is the vessel with the ferrofluid, and here is the belt running. And this is now an experiment performed by Thomas Friedrich during his diploma thesis. And here you see a time-averaged X-ray picture. So this is about 1,000 pictures of X-rays. We have to do as many as this because these iron rods are in the way. I mean, they are absorbing the X-rays. So you have to average a lot in order to get rid of these iron rods. And what you see here is that this propagating wave in the resonance regime is really shifting liquid, because here you have a container, and in that way you have a liquid ramp. You are creating a liquid ramp in that container by this traveling magnetic induction. You can measure the inclination gamma here, and this is what we did. So once again you see this is the inclination gamma as a function of the driving velocity or the driving frequency, and you see that you're getting here a resonance, and this resonance is now shifting again with higher fields to lower frequencies. And here you see again a comparison of this resonant phase velocity with the dispersion relation. And this time we used the nonlinear dispersion relation in a form which is taking into account a more adequate description of the magnetization curve. You have here the nonlinear magnetization curve, which is blue. This is the magnetization as a function of H, and you have to take into account the chord susceptibility, which is the susceptibility you are getting if you are at Z field by making a kind of chord from Z field to 0, and you have to take into account the tangent susceptibility, which is a derivation of the susceptibility at that point. And then you are getting the resonant driving velocity, where μr is the mean permeability, that is the combination of these both susceptibilities of the tangent and the chord susceptibility. And in that way, you can take into account properly the nonlinear magnetization curve of your liquid. And the green curve now is the outcome of this nonlinear dispersion relation. It's not a fitted curve. It is free of any fitting parameters. We only take the parameters from the magnetization curve. And you see that here in this regime it nicely fits. And of course here it doesn't fit any longer, because then we are in the Rosenzweig instability range. So now we have shown that the resonant driving frequency nicely is correlated, can nicely be described by the nonlinear dispersion relation. The question now arises, how strong is this pump? How large is the inclination as a function of the magnetic induction? Not the maximum, but the inclination. And this is I want to show you. These are the measurements. And well, probably, I don't know how much time do I have, 2 minutes or so? Pardon?
You can have 8 minutes.
8 minutes, good, that's good, because Carsten used 10 minutes of my time at least. Anyway, thanks a lot. Well, so I finished with this model. There is something called a ferrohydrodynamic Bernoulli equation. And this is the standard Bernoulli equation plus some magnetic terms. So you here you see a derivative of the velocity. Here you see the pressure drop, and here you see gravitation taking place, and here you have a magnetic term. And if we assume that we have no flow, so we have a balance in this container, which of driving forces and a pressure drop. So this is a simplifying assumption. Then these parts are dropping out. And now we say that we have we are looking only in the dependence of the quantities in x direction. We can also neglect this term, and what remains is a pressure drop. It should be proportional to some efficient magnetization, and this is the derivation of the magnetic field as a function of x. This is so-called Kelvin force. So the gradient of the magnetic field creates a force on magnetizable matter. This is what you see if you apply a gradient field to a ferrofluid. It's immediately attracted towards the direction of the field, of the field gradient. So this is the Kelvin force. Now we have here the iron rods. The iron rods are creating such a kind of magnetic induction, and we assume now that the height of the ferrofluid, if we don't propagate these iron rods, is proportional to this field. And now we assume that in the resonant case, we have in the resonant case, the ferrofluid tries to follow this propagating field. You see, the green field is ahead of the ferrofluid, but the ferrofluid tries to follow this propagating magnetic field. And in this condition, you see that the maximum is here at this point where the gradient of the magnetic field is largest. And this is the case which you are getting for the case that the phase shift between the height and the propagating magnetic field is pi divided by 2. Then you should get, say, maximal Kelvin force, and that is also the case if you have a driven oscillator where resonance takes place. So yes, put in this assumption, and then we further assume that the magnetic induction is proportional to the height of the liquid. That is, if the liquid is higher, there should be a slightly higher induction. And all this, taking into account all this, you can integrate the pressure drop over one period or over one wavelength. This is the Kelvin force. You can just integrate the Kelvin force from here to here, and what you get is the inclination as a function of the magnetization, of the gradient of the magnetic field, of the wave number, of the height difference, and this is the density, and this is the average height of the liquid. So these are the quantities we all know or can measure, and now we compare the simple model with the experiment, and you see that within the orders of measurement error, this model fits somehow or is not completely wrong to our experiment. Of course, we have only here 4 data points, and that is because in this regime we cannot measure easily the height of the liquid anymore, and that is because there's a steepness of the layer is, here we have the Rosenzweig instability, and you cannot measure the inclination of the Rosenzweig instability with a laser. You have to have very shallow waves in order to do so. So within the Rosenzweig instability, we cannot measure the height, and so we cannot make any predictions there. And we can also not use the X-ray measurements here because of the iron rods. So this is now here comparison here is not adequate. So this has been published recently, and eventually I want to see. I want to show you at the end something what is taking place in the regime where you have the Rosenzweig instability and you are still driving this flow. That means what we have looked at in the last minutes or so was we were in the undercritical regime, so we had just a flat layer of ferrofluid, and we were driving this flat layer with this propagating magnetic fields. And now we are crossing this threshold, and we have the Rosenzweig instability, and we are getting now a complex interaction between the Rosenzweig instability and these traveling fields. And instead of showing you a few pictures, I show you a movie. Let's say, see what's going on. Yeah, that's it. So you see now, for small driving velocities, we have just propagating liquid ridges. Now we are increasing the driving velocity. Going further and further. Now you have a complex coexistence of ridges and some spikes, and these spikes are propagating, and now you can see that somehow you get a square regime. Once in a while you get a square regime, and eventually you end up with a hexagonal regime. At very fast driving frequencies, you have again a hexagonal pattern. So that's it. And this is what we can also measure by averaging several thousand pictures. You see here some ridges, then you get here this square-like patterns, and if you're driving very fast, you're getting a hexagonal pattern. Well, this can be understood, this hexagonal pattern, because then you are driving so fast that this liquid doesn't see these modulations anymore, and it cannot follow these fast modulations, and it just feels the average magnetic induction, and then it does its standard hexagonal pattern. So, but the intermediate regime is interesting, that you get a kind of square pattern, which in a regime where you have never have a square regime for constant magnetic inductions. So this is this regime. Here you get the Fourier modes, and within 5 to 7 centimeter per second driving velocity, you get here this L and T mode is high, and this is the squares regime. This is not yet understood, and we are looking for a model. Everybody is welcome to wind up amplitude equations, but this question of spatial temporal driving of patterns is at the moment of quite a lot of interest, because there was a review recently, and this complex, I want to finish with this complex interaction of flows and forms of ferrofluids. And I thank you for your attention, and just want to stress that all this work was done during the last decade also at Experimental Physics 5. This is the chair of Ingo Rehberg in Bayern. So thank you very much for your attention.
Notes, please.
Yes, please.
In our previous slide, you showed the square and the triangle.
Yes.
From the physical point of view, you have a first order phase transition. It should be a coexistence between the square and the hexagon. Did you observe this?
Well, in the movie you see it. Yes. In the movie you see this coexistence. That's true.
Between squares and...
Yes. Yes. But this is an interesting remark. I didn't think about that actually. We had this coexistence between squares and hexagons. You see it in the movie, and you see it also here in the slides. Here you have some regimes where you have some kind of spatial temporal intermittency, like you have some square arrangements here and some ridges here. Yeah. Maybe activates a movie. And you say this is a first order transition.
Yeah.
And why?
Because it seems that you have a difference in the symmetry between the hexagonal and the square. You cannot have a
That's so.
continuous transition.
Yeah, right, okay, yes, that's true, yes. Here you see some squares, and some in between you have some switching to hexagons.
Yes, probably.
Of course, with our measurement technique, we cannot at the moment discriminate because we are just time averaging everything. We can, of course, we can get it out of the movies, but not with the amplitude. But this is an interesting aspect. I'm grateful for that. Yes, that's interesting.
In this process, the shape of the nanoparticles itself changes or not?
No, I wouldn't say so. I mean, the shape of the particles.
They are solid balls or something? Or
Pardon?
they are solid balls or you can think in this
Well, here we are. Let me think. What kind of liquid are we using? I think that's also kerosene-based liquid here. So, it's anyway no water-based liquid. But I mean, here we are really in a macroscopic regime. Everything what is together with Rosenzweig and these small modulations of the field is somehow macroscopic, and so it's not so really not so, how to say, sensible to these agglomeration processes like this stuff with a fast rotating or fast alternating field, where you have all this very tiny, this tiny relaxation times of these fast frequencies. I mean, this Brownian relaxation times is in the 10 to the minus 3 or something seconds. So it's in the inverse in the kilohertz regime. There, everything is very sensible to the size of the aggregates and so on. Here, not. Here you have just some kind of almost static magnetization curve. Here the complex susceptibility is of no importance. Yeah. So that's quite a difference between, for example, this ferrohydrodynamic pumping is in the kilohertz regime, and we are here in the millihertz regime. Yeah. So I just want to cite Thomas Friedrich, who is always claiming here, well, we have a magnetic pump, but you cannot cool a power station with it. So these are very tiny forces, and it is of academic interest. It's not of industrial interest here. But some of these pumps or aspects I've shown you with this propagating droplet is maybe of interest in this kind of lab on a chip applications, where you want to transport tiny amounts of liquid from one part of your chip to another, and because you can control that with a joystick by just controlling the rotating fields. And for that tiny applications, that's interesting, but not for here cooling power stations or your heating systems or so. This is very inefficient here, I think.
More questions?
Here.
Yes, please.
Do you use some technique, any technique to determine the size of particles?
Which techniques one can use to determine the size of the particles? Yeah, there are different techniques. One is X-ray diffraction. Another technique is you make transmission electron microscope pictures. So you have a small film of ferrofluid. you dry it on the spacer. That is a disadvantage. You have to dry it, and then you go into the vacuum of your transmission electron microscope, and then you take a picture and you make image analysis. This gives you something of a kind of an estimate for the hydrodynamic volume fraction. And but it is very rather vague, because you have to know that your ferrofluid is somehow thin enough that you don't get particles on top of each other and so on. Then there is light scattering. There are light scattering techniques, where you can also get some. I mean, these are standard devices, synthesizer, and these things. Probably you have in your department. Let me think, what else is possible? Birefringence is possible, yeah, we didn't do that ever. Yeah. Well, to be honest, it is always a bit cumbersome with these microscopic pictures, because you have always this distribution of the particle sizes. And as I've shown you, sometimes you get also field-dependent agglomerates, which is really making the situation quite difficult.
Do you have any idea of the size of these aggregates that it's being formed? How big they are? I mean, hundreds of particles, dozens of...
No, it shouldn't be so. It depends on the material, of course, on the ferrofluid. Yeah. There have been, well, in this kind of magnetite also, the coupling parameter is rarely above 4 or something. So, well, it's actually difficult, because one has to discriminate between the standard magnetic particle and something which is called primary agglomerates. And these are some kind of artifacts during the production process. So if you have a standard magnetic particle, like in a water-based or another ferrofluid, with tenside, you have such a kind of particle, and then you have another particle, and they are preventing, they cannot move too close to each other because of these tenside layers. But it happens that during the production process something is created which is called a primary agglomerate, which means that these particles are agglomerates and later covered by the tensides. These are these guys. And especially in water-based ferrofluids you're getting these guys. And they may be only 0.1% or even less, but they are huge compared to the standard particles, because as I've shown you here in some of these slides, where is it? This here. Here you see that you have here this exponent. So that the size is really somehow, this is very sensitive on the size. And it can be that these particles are already so small that the Neal relaxation time is dominant, is important, so they are not Neal blocked. But the combination of two of these guys to a primary agglomerate then are so large that you have a larger magnetic volume and you are over this exponential. I mean, you are already in over 1 here, and then you contribute a lot. And this makes it so difficult with this. I mean, with this microscopic description, and especially with this water-based ferrofluids, because they tend to agglomerate.
More questions?
But here you have experts in X-ray diffraction, and
I was thinking about maybe we can try to investigate this using small angle X-ray.
yes, this is a common technique to use that.
If you investigate this before applying your field, you can more or less quantify these big particles, and then later on when you put your field by this difference, you can figure out what
Yes.
has changed.
Yes.
So we can talk about it.
Yeah. Well, there have been studies on this kind of agglomerates in Grenoble and also in Desi in Berlin. By several groups. You need to, you can get chains with a large number of particles, and then you have a problem because you are in the regime next to your beamstop. That means this is it's not so easy to resolve, but there have been a lot of work on that topic. We did not contribute anything to that because you have to be very good in scattering theory, and also in you need large machinery. But maybe you look at papers by the group of Wiedemann. They did this scattering studies with cobalt particles, and cobalt tends to make chains because of this very strong because of this very strong magnetizations and so on. Yeah. And so you get chains in cobalt, and you get even magnetorological effects in cobalt ferrofluids. And this book, which we published in, I think, 2008 or something, in a collection of articles on ferrofluids in Springer. I've mentioned yesterday, it's colloidal magnetic fluids, blah, 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 blah. By Odenbach is the editor. You have chapters on specific questions of the scattering problems. So people were looking on shear flow, and they looked how this scattering is changed by the shear flow in magnetic fields. So I would say there has been a lot of things has been done, but certainly it's always good if you have the opportunity to analyze your liquid locally by scattering techniques. That helps a lot.
Okay, let's think again.